Okay, let's get started here. So project number 1 was graded and emailed back to all of you. We'll discuss it briefly at the beginning of class. Project number 2, I posted it this afternoon. We won't have time to talk about it today, but definitely will on Thursday. A very tentative due date for project number 2 is Thursday, September 27th. I really like to grade it before test number 1, but we need to have test number 1 too. So, sometimes it's hard to work out, get the projects to align with the tests, or have all the projects done before the corresponding material on the tests is needed, and I don't know if we're going to be able to unfortunately do that. So we will see. Are there any questions before we get going here? Okay, so let's briefly talk about the project. So given that the test is coming up, I'm starting to think about what's important to test you on. And so when I was taking a look at the project then, I was thinking, well, what do I want you to get out of it? And so I just thought real briefly to summarize some of the big points that I wanted you to get out of the project. And hopefully you understand this, but sometimes it's helpful for a professor, I think, to summarize what I thought was the big points I wanted you to get out of it. And, first of all, on number 1, we had a very small data set. And I wanted you to understand, the distribution of T star, the exact distribution without actually doing a resample. If we could, we would always do everything this way. But since there's just so many different combinations of the data, it's usually impossible in most applications to actually get the actual distribution of T star. But if you do get that, then you can find then the exact value of the expected value star T star, and also the exact value of the variance star T star as well. Just from using basic definitions of what a probability distribution is. Then 2 and 3 approach the problem. I guess let's talk about 2 first. Obviously, 2 was dealing with the parametric bootstrap. And this is a little bit like 1 in terms of you can get the actual distribution of T star. Well, if you can get that, then you should be able to understand concepts like, well, what is the actual variance, var star T star, and also how we can actually estimate this using R resamples. Then lastly, on number 3, now we talk about the non-parametric bootstrap. And again, for this particular problem, you are actually able to come up with an exact calculation of what var star T star is. And also, through actually taking resamples, you can estimate it too. And the big picture then of why we're interested in these variances is because we want to estimate the variance of T. That's the whole goal. Now also, there are other important things with this project too, such as you had your first exposure to confidence intervals, the basic and the studentized confidence intervals. You should expect at least one of them on the exam, and maybe you might have to do some quick derivations in terms of the parametric setting, or it might be just all non-parametric as well. Be familiar with how you can find Z star. I might ask you, well, give me the actual Z star quantile. So don't just necessarily rely on boot.ci. Now, obviously, boot.ci makes things easier. You should know how to use it. but make sure you can actually get the corresponding interval without boot.ci. And there's one other thing I wanted to highlight with this project. If we have it, if we turn to it's problem number 2, part H. So in this case, I wanted you to actually derive the basic bootstrap confidence interval sigma squared using parametric bootstrap. There are 2 ways to do it. I did it the harder way first. And then the second way is the way that everyone else did it, which is totally fine with me. But I want to talk about the harder way first because it contains a number of basic concepts of how to use R that will be useful later on when the easier way may not necessarily be available. So we needed to derive a actual confidence interval, basic bootstrap confidence interval. And so this is the actual formula that was originally presented. And the thing that we're going to do is actually replace f with f hat. Okay. Now, this G is the distribution of t minus theta. So then, if I put a hat on top of the f, I'm looking for the distribution of t star minus t. We know what the distribution is of t star based upon, remember t is regular old sample variance. We're sampling from a normal. So t star would be, let's say, s squared star, and it has that corresponding gamma distribution, which all of you were able to get. But what's the distribution of t star minus t? Well, let's just make this notation easy. How about we call that random variable b? Well, one could apply STAT 883 concepts. I'm sorry, 882 concepts to actually, find a Jacobian, get what you need, and come up with the actual distribution. So it's a little bit like a kind of a shifted gamma, essentially. So after all, this is just a constant. And the support for the distribution is negative c to infinity, where c is equal to t. I just wanted to get t totally out of there to avoid confusion, so that's why I put a c there. So this is the distribution of t star minus t. And so again, what I want is to be able to get a 1 minus alpha quantile from this distribution and also an alpha quantile from the distribution. First of all, I need to be able to program in the distribution in R. So this is where some of the basic ideas of how to use R come about. So I just need to put everything into the correct syntax, and I'll let you look at the syntax on your own of this distribution into R. I create a function that calculates basically the density function evaluated at a particular point. Let's call it B. So you can think of this as returning f of B in the end. And if I wanted to, I could use then the curve function to actually plot the distribution as well. And this is what the distribution looks like. As a nice little verification that indeed that I did everything right. Well, I guess this isn't a guarantee that I did everything right in terms of the derivation of the distribution. This is a nice thing to have happen. And that is, if I were to integrate this distribution over the support, I should get 1. This is probability distribution. And so how do I integrate in R? I use the integrate function. And so I say, where's my function that actually calculates then the density? So dist.b. I want to integrate over negative t to infinity. Notice how I actually represent infinity in R. Subdivisions equal 1,000. Anybody know what that means? Do numerical integration here. Yeah, how many little chunks I take when I do my integration. In other words, you can think of it this way: I'm finding a whole bunch of rectangles, and I'm finding the area underneath the rectangle. Okay. I could have went with the default of 100. Actually, I was copying and pasting some code from some other time when I've done some integration recently, and I used 1,000, so that's how that ended up being there. I put in alpha, I put in beta, constants, that's C, and look at this, integrates to 1, so great. Okay. Now remember, the whole purpose of us doing this is that we want to find quantiles from our distribution. So we want alpha there, we want alpha there. We want to know what numbers on this x-axis gives us that. So what one could do, again, is use the integrate function, integrate from negative t up to maybe try negative 4, and see if this gives me, let's say, 0.025. I'm finding 95%. If it doesn't, then increase or decrease your value that you're having on this axis until you get to 0.025. You could do exactly the same thing over here as well. Alternatively, what you could do is use a root finding function. This is, I guess, another basic application of stuff in R that can be very useful. So what I have here is, let's say I set this equal to 0.025. I want to integrate from negative t to my quantile, let's call it Q alpha, of my distribution. I want to find Q of alpha. Or in other words, I want to find 0.025 minus the integral, set it equal to 0, find the root. There's a variety of root finding methods out there. If you've taken a numerical methods class as an undergraduate, you should be familiar with like a bisection method, or there's various other ones that are faster than that. And in R, a nice easy way to do this root finding method is use the unit root function. So the first thing I need to do is program in this into R. So I have a function called root.func. I save the results from doing the integration like I just did before. Notice I'm going to integrate up to q.alpha, and also that is the very first argument there. And then I pull out the integral value, subtract off whatever alpha level I've set, like 0.025, and this will then allow me to use unit roots. So I say unit root, root.func. What's the integral that I want to look over? Negative t to 0. I picked 0 because I thought by the time I get to 0, I probably reach 0.025. Definitely. Alpha level 0.025. I also had to pass in y, my data. And this is what it gives me, negative 3.5. So this is q 0.025. So the 0.025 quantile from this distribution is negative 3.5. What is f of b at that particular value? Or I'm sorry, this gives me basically this right here, 0. So that's what this function's evaluated at. It took 9 iterations to do it. I can do a similar thing for this upper quantile from the distribution. Note that there's a small error in the answer key. I should have put instead of 0, instead of negative t there, I should have put 0. So I'm going to search from 0 to 20 for the root. So that's the basic things I wanted to say about this. I hope you take some time to look it over to make sure you understand it, because doing integrals, finding roots are going to come in handy later in this course. And also, so many things that you do in statistics involve integrals and also finding roots. Here are some very general numerical methods that can do that for you. So I imagine that this can be very useful to you outside this class. Are there any questions about that? Yes.
I had a question in the beginning of the, if you scroll up to where you discussed the derivation.
Yes.
On the second line, should either of those F's have hats on them? Because if we're talking
You mean this right here?
Yeah, so the line that starts with where,
Okay.
and then there's those two G's.
Yeah.
They should have.
Yeah, it should have.
Okay.
Yep. Thank you. Delete that part too. Are there other questions? Okay. Let's see. Is there anything else I wanted to say too? So, overall, grade-wise, it's pretty good. The mean score was 62 out of 70 points. Just be careful with your notation. Make sure you use the same notation I'm using in class, because it can be difficult for me to understand what you're talking about if you're not using the correct notation. Any other questions? Okay, so we left off last time about page 216. So we were looking at cases. When does the bootstrap not work? Well, what do we mean by it doesn't work? Well, this particular section of the book talks about it in terms of as n goes to infinity. It seems like a reasonable thing, because you would hope that as n gets big, that whatever statistical method you're using is doing what it should do, or gets better, you could say. And we were looking at a specific example where the bootstrap is not working as we had intended, where we had data that came from a uniform 0 theta. And we know the maximum likely estimate for, in this particular case, for theta would be the nth order statistic. And in this kind of a case, one could show that Q is equal to n theta minus y sub n divided by theta converges in distribution to an exponential 1. I'm sorry, exponential theta. We let theta equal 1 just so that we had an actual numerical value for our actual example that we did in ARM. And so what this basically represents is if you know what f is, then you know what the actual sampling distribution is for your statistic of interest. We call it Q. No, we'll just call it Q. And what you would hope then is if when you do this with the bootstrap, then, you would hope that you would get the same thing. As n goes to infinity, you reach that asymptotic distribution. Unfortunately, we don't. So we saw this, for example, this is the EDF plot from actually taking resamples. And I think this was for n equal 5,000. And up also plotted there is the exponential 1 in red, and we can see that we don't get there. If you turn to page 17, we have a little bit more of an explanation of what's going on here. So we know that the asymptotic distribution for Q is obviously a continuous distribution. So Q star, if everything's working out right, should be a continuous distribution as well. What that means then, of course, with a continuous distribution, any kind of probability that you're equal to one particular value should be 0. Or it should go to 0 as it gets big, in this case. But instead, the probability that Q star is equal to, let's say, 0 itself. I could have picked a different number, but I'm following what the book did. The probability that Q star is equal to 0, given f hat, ends up being not equal to 0. Again, if we had a continuous distribution, then this value should be equal to 0. Now, just for emphasis, here's Q star again. Now, when Q star is equal to 0, that means T star is equal to T. So we could equivalently look at it like this. The probability of T star is equal to T. Or what's actually going to be a little bit easier for us to do is look at it in terms of the complement. So 1 minus the probability T star is not equal to T. Well, what is this probability then? What is this probability? Well, there's only one way that T itself can be the nth order statistic. Okay? I'm sorry, there's only one way that T star can be equal to the nth order statistic if it ends up being in the resample. So that means then for every element in your resample, the probability is n minus 1 over n that it's not equal to y sub n. Since you have n elements in your sample then, in your resample, we have n minus 1 divided by n raised to the nth power as that probability. So if we work with the complement then, notice things simplify down to 1 minus the quantity 1 minus 1 over n to the nth power. Well, what happens as n goes to infinity? 1 minus e to the negative 1 using a cap 2. That is obviously not equal to 0. And thus, Bootstrap's not working. I guess, again, for emphasis with this additional bullet here, I just remind you that we know that this sampling distribution is an exponential 1 for n as n goes to infinity. And so what's happening here is that we're not having this part. But what if though we do the what if we do the parametric bootstrap instead? Well, in the parametric bootstrap setting, again, this is on page 16 again. I'm sorry to be bouncing around here. It's on the bottom of the page. Similar code to what we've seen before, so I'm not going to go into it. Just note that I'm using the RUnif function to do my resamples. I'm going to get 2,000 resamples. And notice that I'm resampling from basically a uniform 0 nth order statistic. Y star distributed that. And if I find my Q for every single resample, look what happens. Plot exponential 1 in red, and the distribution from the bootstrap for Q star is in black. You can see things are working out. So it does work in this case for parametric setting. Note that overall, with the non-parametric bootstrap, since we're starting from a discrete distribution as f hat or EDF, it's always going to have problems when you're working with fixed order statistics. These fixed order statistics themselves are not what are referred to as smooth statistics. They're fixed in place, and that's the problem. Okay. So let's go on to a new topic. This is going to be a brief topic. Talk about Edgeworth expansions. All of you have seen Taylor series expansions before. Just a quick review. Let's say that I have some kind of function of x, f of x, and I could write this as an infinite series. Let's say f of b, where b is some constant, plus x minus b raised to the 1 power over 1 factorial times the first derivative of f of b plus, let's just do one more term, x minus b raised to the second power over 2 factorial times f second derivative evaluated at b. And you can keep on going. Okay? So it's just a way to write a particular function as an infinite series. Oftentimes, you will see this too, where we actually write this as f of x minus f of b is equal to this, cheat, the yellow part. I sure hope all of you brought your colorful pens in class today to write notes. Now, if you take a set like 980 course, you learn that these Taylor series expansions are really nice because often you're working with a statistic and you want to approximate that statistic with something that's a little bit simpler. So, for example here, if I want to approximate, if we go back to the idea of approximating a particular function, if I want to approximate this function, what I could do simply is take these terms and get an approximation for it. Now, with asymptotic statistics, so much of it relies on, let's say I have some function of my statistic, let's say t, I could use a Taylor series expansion and say that it's equal to g of theta plus t minus theta room times first derivative of g of theta. I'm sorry, first derivative of g of t evaluated at theta. Does anyone need me to rewrite that? So the hope then is that when you rewrite a function of a statistic like this, the stuff that's on the right-hand side is easier to work with, and that it's more easier to find than the actual distribution of the stuff on the right side. That gives you an approximation for the distribution on the left side. It's a lot of the big stuff that you do in asymptotic. So as n goes to infinity, hopefully all the stuff that you've left off, in terms of, let's say, like this kind of stuff, is not meaningful. Well, Edgeworth expansions work like Taylor series expansions, except for now, what you're doing is approximating probability distributions. And this approximation is written in terms of a standard normal. Now, the goal for this little talk about Edgeworth expansions here is for you to have an understanding what Edgeworth expansions are and its use in the Bootstrap. I'm not going to ask you on a test to perform an Edgeworth expansion. My brief explanation here follows some stuff that was in Ferguson 96's book. Okay. So let's say that we have a situation such as we have x1 through xn or iid, each have a mean of mu and a variance of sigma squared. Now by the central limit theorem, we all know that the square root of n times t sub n, where t sub n, let's say, is my x bar, minus mu divided by sigma is approximated by normal 0, 1. So I purposely, instead of putting x bar in there, I purposely put t, because that's often what we are using in this class, and I purposely put a subscript in there to emphasize that This is dependent upon your sample size. So again, we know that this is approximated by a standard normal. Equivalently, we could say that the CDF for this quantity is approximated by the CDF of the standard normal. How about we just simply call that G of T, where I emphasize the N there, dependence on N. Now, I guess I will ask this question again for those who have 980. Did you talk about Edgeworth Expansions? But you did talk about central limit theorem, all that good stuff, Lindenberg, Feller, all that. Now, what you guys don't learn, and what others in this class probably don't know, is that we can make this approximation better. So again, G of T is CDF of this guy up here. What you learn from the central limit theorem, it's a standard normal. Standard normal CDF. But one can keep on going and look at additional terms in the corresponding expansion to this distribution. The first, I guess what's often referred to as the second term of the expansion, depends upon, this is the density function of a standard normal. Beta 1 here is the skewness of X. The third term in expansion, again, has a standard normal. You have the skewness, but now you also have the kurtosis as well. So if I have more terms in this expansion to approximate the distribution, do you think this is going to end up resulting in a better approximation for the distribution, or worse? Better. We'll see that shortly. Now, in the book talks about Edgeworth expansions, but really doesn't, unfortunately, doesn't get into details of it. It expects that you know what Edgeworth expansions are before you read the book, which isn't necessarily good. But when they talk about Edgeworth expansions, they write them in terms of cumulants. You heard of a cumulant generating function set 882? Some of you, yes. Cumulant generating functions are great. If you don't remember what they are, essentially they're just this. Log of your moment generating function. That's it. So with a moment generating function, you know, if you take the derivative with respect to t, set t equals 0, you get the mean. If you take the second derivative of the moment generating function, set t equals 0, you get the second moment, in other words, like expected value of x squared. What happens when we do this? Those of you who remember. What's that equal to? The mean, yeah. What happens if I do this? It's supposed to be a second derivative. The variance, yes. So this is always a shortcut to finding the variance. Well, you could look at this in more detail for higher cumulants, and these are then cumulants. You can look at it for higher order ones as well, in terms of the skewness, in terms of the kurtosis. And you're going to see the book even have a little appendix about that aspect of a cumulant generating function. And often these Edgeworth expansions are written in those kinds of terms. Okay, so let's take a look at a quick example of how this can help. Let's say that I have sample size of 5 from an exponential, just to make things easy. And it's exponential 1. And what I'm going to need are some higher order moments. I could do them all by hand, but given that we have symbolic mathematical software, why shouldn't we do that? Anyone have experience with Maple? In 882, 883, do they talk about how to use mathematical symbolic software? Okay. Well, if you look at the end of Cassellenberger's book, they talk about it. If you want more information. I'm not going to go into the details then, but here's just some simple Maple code. You can think of it as just example of how easy doing all this math can be. So, of course, with an exponential, x is greater than 0. Using the Maple syntax, I program in the distribution. I simply find the mean, by using an int function for integrate. If you want to do it all symbolically, you just take off this part there. I can also find sigma squared, as you would kind of expect. And then beta 1 and beta 2 are the corresponding skewness and kurtosis as well. So, real quick. You can also program all this into R2 if you really wanted to using the integrate function. I'll leave the details here for you to look at in terms of what I need to do next is basically put into R syntax this approximation. And let's just focus on the plot at the end. Blow this up as well. Okay. So, although it's kind of hard to see, there is a black line. Follow basically the green line. You're going to see the black line. And that black line is the actual exact distribution for what we had seen before, square root of n t minus mu sigma, written in terms of exponential. This ends up being a gamma. Now, the central limit theorem, so this is the CDF part, sorry, I didn't say that. The central limit theorem gives you what's in red here. So just a standard normal. Obviously, that's not necessarily the best approximation for what the true distribution is. So let's look at Edgeworth 1. And my labeling is not the best here, so this uses two terms. So it uses the CDF of the standard normal, plus then that first term that was dependent upon of only the skewness. And we can see with the blue line, that's getting a lot closer to the black line. A better approximation. And if I go up to 3 terms, that's what's done by Edgeworth 2, you see that practically the green line for Edgeworth 2 is right on top of the black line for the exact result. So you can see how this tool can be very powerful with approximating the distributions of a particular statistic. Remember that sample size was 5 here, so you wouldn't expect the central limit theorem necessarily to do a good job. But with extra terms, you can get a better approximation. Okay, so page 24 then. So what role does Edgeworth expansion serve then with Bootstrap? Well, I just told you that these Edgeworth expansions allow you to approximate a distribution in terms of simple normal distributions. Well, the underlying theory then for the Bootstrap and how it works then relies on basically doing these Edgeworth expansions that instead of, let's say, working with f itself, work with f hat. And by doing that, then, you can get an approximation of g hat and show that this g hat is approximately then the same, or goes to, I should say, g of infinity. Or as n goes to infinity, that particular distribution. That's why Edgeworth expansions are used. If you have an interest in the mathematics behind all that, take a look at Peter Hall's book. Chapter 2 is the introduction to Edgeworth expansions. Then he actually goes through all the mathematical proofs behind why Bootstrap works. Some more stuff on Edgeworth expansions. Actually, Cassellenberger does a little bit. It sounds like none of you actually got up to page 517 of the book. Another great resource is David Hunter's course on asymptotics at Penn State. This is a required class for their stat students, their PhD students. Excellent set of notes he has there. There's a lot of stuff that's different from what you would expect in like our Stat 980 course, just to let you know. And just a few other references as well. Any questions? Okay. Why don't you take out this rate to the convergence document. We're not going to spend a whole lot of time on it. It's quite short. A lot of these things should be familiar. I think sometimes in a calculus class you see what's called little o and big O notation. Who has not seen little o and big O notation? So all of you have seen it. So maybe I don't need to do this. Okay, thank you. Thank you for your courage to say something. I anticipate that some of you, it's been a while since you've done that, seen it, so that's why I purposely wrote up this set of notes. There's also some stuff here that you may not have seen before in terms of how this big O and little o notation works in terms of how we use it in statistics. In 980, do you do big OP, little OP?
There were
We've had O's.
In Casella, in 883, do you ever talk about big OP, little OP? Okay.
Never had a P linked with it.
Okay. P stands for probability. Since we're in statistics, we were concerned about stuff in probability. So, let's talk about this. Simply, if I have something A sub n, so it's A's, let's say, dependent upon n. For us, eventually, n is going to be our sample size. Divided by B sub n. If that goes to 0, as n goes to infinity, we can write this in terms of what's called little o notation. And simply, we could say A sub n is equal to little o of B sub n. It's just notation. That's all it is. Just notation. O is for order of convergence. So, for example, let's let A sub n be 1 over n squared, B sub n be 1 over n. If I take A sub n over B sub n, obviously that's going to 0 as n goes to infinity. So in I guess a very general notation, people often then represent this as A sub n is equal to little o B sub n. Alternatively, you'll see people write it like this. 1 divided by n squared is equal to little o 1 over n. Or equivalently, you can say A sub n is equal to little o 1 over n. Obviously here, A sub n goes to 0 faster than B sub n. Some people might say A sub n is an order of magnitude smaller than B sub n. Just to emphasize this, well, how fast is this working out? Well, I just plugged in some numbers there, and you can see how 1 over n squared, which is the A sub n, is indeed going to 0 faster. Okay. Here's another example. Suppose we have A sub n is equal to 1 over n minus 2 over n squared plus 4 over n cubed. You often see stuff written like this. A sub n is equal to 1 over n plus some kind of remainder term, where the remainder term was everything else that was in that original A sub n. And the reason why you see that is because this part is playing a much smaller role in determining what A sub n is than the 1 over n part. Because that stuff that's in the remainder is going to 0 faster. So what you will see sometimes is this. R sub n can be written as little o 1 over n, so that then A sub n will be written as 1 over n plus little o 1 over n. So all this is saying then is that the remaining stuff that you have here, this helps you determine basically the order of convergence. It's going to 0. Oh, we're not as concerned about it because it's going to 0 faster than just 1 over n itself. You could also write this then as just take the first two terms, and then the last term, remember that had an n cubed in it? The last term is little o 1 over n squared. One could say then just using 1 over n itself as it is maybe an approximation to what a sub n is. If we took the first two terms, it's also another approximation. We'll say it's a second order approximation. Obviously, if you took all three terms, you get a sub n. But because of the stuff's going to 0 fast, you might be able to get away with just the first or the second term. Let's talk about big O notation. A sub n divided by b sub n, an absolute value. If that is bounded by a constant, it's called m, then we can write this as a sub n is equal to big O of b sub n. Just notation. So, for example, excuse me. Let's let a sub n be equal to now this, I'm not going to read this all out, this function of n. Then we could say a sub n is equal to 1 over n plus some kind of remainder term. This remainder term, then, you could say is big O 1 over n squared if b is equal to 0. So that if you only had to worry about this, notice the main thing, the thing that's most important here, the n squared. So that's why that part there is bounded by a constant. Constant c. Now you could get a little o 1 over n squared instead if both b and c is equal to 0. Notice if b and c were not equal to 0, then you're going to have something that's going off to infinity. Okay. So, one of the main reasons why we look at this kind of stuff for our class is to understand the answer to this question. Suppose you have two different approximations to an that you could choose. An is equal to bn plus a little o 1 over n, or an is equal to cn plus little o 1 over n squared. And you want to either use bn or cn to approximate an. Which would you prefer? Cn. Because this part here is going to 0 fast. Going to 0 fast is important in statistics. When we start talking about approximating the distribution of a particular statistic. So let's extend this concept of rates of convergence to random variables. This comes from Cassell and Berger's book, Convergence in Probability. Simply, let's say that I have some random variable x sub n. It converges to another variable which we are going to call x. It's not dependent upon n at all. Your sample size, n is your sample size. Sorry if I didn't say that. Then, x of n converges to x in probability if the following holds true. The limit as n goes to infinity of the probability that the distance between xn and x gets small for some epsilon greater than 0. If this whole probability is equal to 1. That's convergence in probability. And we can write this as xn converges in probability x. So a little line there with a little p on top. Now, if we have two random variables, let's call one a sub n, one called b sub n. I'm now using capital letters here because we have random variables. These random variables are dependent upon your sample size. And if I look at the ratio of A sub n and B sub n, if that converges in probability to 0, then I can write it the following. A sub n is equal to little op of B sub n. I put a P on O because now we're talking about probabilities. So where can this be useful? Well, again, often in an asymptotic course, you have some kind of maybe complicated statistic that's dependent upon n. And you can approximate it by at least a lesser complicated statistic that perhaps maybe you know the distribution of. It's called B sub n. But you always have to worry about that there's probably going to be some kind of extra stuff out there. That's called R sub n. That's your remainder term. If R sub n converges in probability to 0, then you write the following. A sub n is equal to B sub n plus little op of 1. So take R sub n divided by 1. You'll see this notation in statistical journal articles all the time. This is a little op notation. All this is saying is it gives you some measure of, well, what is that remainder term? And as long as this is going to 0, then you could use B sub n then to approximate the distribution of A sub n as a moves to infinity.
Why is it op of 1?
So take B sub n to be 1.
Okay.
You could also talk about big O sub p notation. So, basically this is the same idea that we have this stuff that's bounded. We have these two random variables that, when you take the ratio, they are bounded by some constant. As n goes to infinity, bounded in probability, then one could write x, big O sub p, sorry, I'm not saying it very well. A sub n is equal to big O sub p of B sub n. So for example, you might see something like this often. X sub n is equal to big O sub p n raised to the d power. That tell you again, what's happening in terms of this convergence. Now note that this is just a constant. So equivalently, we could write it like this. X sub n is equal to little o sub p of n sub n raised to the d plus delta power, where delta is something greater than 0. So you'll see this kind of notation interchanged. You get big O, now take a little bit higher order for your n in terms of the power there, you get little o. So again, why are we looking at this? Suppose you have two different ways to approximate a statistic A sub n. Statistic, of course, statistics are random variables. One has a remainder term that's little o sub p, 1 over n. One has a remainder term little o sub p, 1 over n squared. Which would you prefer, C sub n or B sub n to approximate A sub n? C sub n. So we want this one. So again, why is this important? Well, frequently it's a lot easier to find a distribution using an approximation to a statistic rather than the statistic directly. You'll see this type of notation used in statistical papers everywhere. Just pick up a JAZA and you'll see it. Pick up an ANOS, you get scared with how often you see it. What are we looking at? Well, you need to be able to read material in our book when this is used. Don't worry about doing the proofs when you see it. Just understand the basic concepts of what it means. So where are we going to use this first? Page 25. Okay. So how far off then is the resampling distribution of the statistic in comparison to the true distribution? If Q, so Q's are statistic of interest, suppose it's pivotal. then CDF of Q star minus the CDF of Q evaluated the same point is big OP 1 over N. If Q is not pivotal, then look what happens. Get a little bit slower convergence. So, given the choice between a pivotal or a non-pivotal thing, which would you prefer? Pivotal. How are these kinds of results proved? Through Edgeworth Expansions. There's some other, yes?
Oh, sorry,
Oh,
I
you're
was
just
pulling
stretching.
up my
Okay.
sleeve.
Please read this on your own. Just talk some more stuff about when you're working with on tiles. There's different ways that you can do this using Cornish-Fisher expansions. Also, coverage for a bootstrap confidence interval. This is going to be a more important topic in Chapter 5. When you're working with pivotal, it's better. Okay, I think we talked about the first bullet here, page 26. And I think we pretty much covered page 27 when the bootstrap doesn't work. Note that we need the IID assumption to work with Y's. If you don't have the independence part of the IID, you can have some problems. For example, if you have time series data, or you have observations that are collected, let's say, over time 1, time 2, time 3, you can't do what we're doing exactly. Chapter 8 discusses what you can do. There's been a lot of research done on that. And also, if you're sampling from finite populations, well, it causes some dependence amongst the Y's. And what can you do? There's some stuff in section 3.7 that allow you to do some fixes too. So, okay, page 28 then. We're going to start off with, this is section 2.7. This is, I think, really the main part of this part 2 notes. The section actually doesn't talk about the bootstrap a whole lot. It's going to give 3 non-bootstrap ways to estimate the variance of T. Now you might be thinking, well, geez, we've already been talking about how to estimate the variance of T. Why do we need non-bootstrap ways? Well, as you'll see, it comes in handy. So we'll talk about 3 ways to approximate the variance of T. And we'll also talk about, at the very end, a 4th way, which actually involves something called the double bootstrap, which I briefly mentioned in class before. To begin, though, to understand how we're going to do this, we need to review the delta method. We've briefly talked about the delta method before, but I want to talk a little bit more about it, and also how the delta method comes about. Sorry to keep on doing this, but in set 883, did you ever talk about the derivation of the delta method, or just apply it? Just applied it? It's important to understand. The derivation is rather simple. It's important to understand how it comes about to motivate in what we're going to be doing with what's called the non-parametric delta method. So you can think of what we're doing right now is called the parametric delta method. Although we usually don't ever call it that. Some terminology to help you out too, because you'll see this in the book, you'll see this in other places too. People often refer to doing delta method approximations as linearization. So essentially what you're doing is you're doing a linear approximation to a function. Taylor series expansion. C. Okay. The delta method explanation that the book gives, I don't think it's necessarily the best. They could have made it simpler. So this is my explanation of the delta method using their notations. So if you don't like the notations, you can still blame them. Let's say I have a statistic of interest U. I have some parameter. Anybody know what this Greek letter is? What's that? Really? I've never heard of that one before. Well, if you look it up on Wikipedia, of course, we trust it. It's called sigma? Well, we already have a sigma. We have two other sigmas. So I guess the Greeks, they like to duplicate their notation, and they like to have additional symbols to mean exactly the same thing. Instead, what I'm going to call it, I guess I would pronounce that as xi.
Maybe where I came up with
Maybe I should just call it cassis. I'm going to call it xi because it's very, very close in a symbol. So, for example, if I pull up map type here, and I know this is probably small, but you can see, let me move this up. So you have all these symbols here. Here's the sigma right next to this sigma. So they're both two lowercase sigmas, supposedly. But notice what it says here. It might be kind of small. It says a final sigma. Sigma. Okay, whatever. But it looks very similar to the Greek letter xi. So I'm going to call it xi. If you want to call it something else, you can do it outside of this class. I'm going to call it xi. So you estimate xi, and let's say somehow we know that square root of n times u minus xi converges the distribution to some random variable x, which has a normal distribution between 0 and a variance sigma squared that's perhaps dependent upon xi. Often what you're interested in looking at, though, is some kind of function of your statistic of interest. Let's call this t. And maybe, this is using the book's notation, suppose this function is g of u. So we use g here to mean our function of u. Also, we could, and the purpose of this then will be to estimate then something called theta, and it's a function of psi. So what the delta method says then is that the square root of n, g of u minus g of psi converges the distribution to the first derivative of g of u evaluated at psi times x. Or in other words, using the basics of what a normal distribution is and working with that, a normal 0 g first derivative evaluated at psi squared times sigma squared. Well, where does this come from? It's just a Taylor series expansion. That's all. I talked about Taylor series expansions earlier today on purpose. Let me actually do a split screen. Where are you, Taylor series? Here. Yeah. What is a mess? Do some erasing. There we go. So, there's a regular old Taylor series expansion. So instead of saying f of x here, now I'm going to say g of u. I use equal with a dot on it to emphasize approximately. G of psi, so that's my f of b, plus u minus psi, first derivative of g of u evaluated at psi. Okay? People refer to this as a first-order Taylor series expansion because we're basically using the first derivative. That we're using the first thing after just evaluating the function at psi. Of course, if one wanted to, one could keep on going, do a second order, a third order, fourth order Taylor series expansion. You can imagine that you're probably going to get better. Well, you'll see some asymptotics books talk about that, but usually in statistics we do so much stuff it's just only first order. So when I have that first order expansion, then what I can do is rewrite this. Let's make that go away. I can rewrite this so that I move then this part over to the left-hand side. So I have g of u minus g of psi is equal to that down there. How about we multiply both sides by the square root of n? The reason why we do that then, because we know what the distribution of this is right here. Normal 0 sigma squared. Well, what do I do with this little derivative there? Well, that's where you apply rigor, old, working with a normal, and you pull that inside the normal as a square. This is the derivation of a delta. Right. Not too difficult. Any questions? And this is a basic stuff that you do in like in a 980, like set 980, let's say, doing little approximations like this. Okay. Yeah.
So the second square and then parentheses side. Why is the parentheses side?
All it is to emphasize it's a function of your unknown parameter. That's all. I know that it can be a little confusing because you might be thinking I'm multiplying. No, it just means a function. It's very similar to what we were looking at last week when we were working with when we did the confidence interval for proportion. Okay. Okay. Well, I think this is a good place to stop. Because this next stuff, I want to do it all at once, and it takes 4 pages to get through. Are there any questions? Yes.
I have a question from back to section 2.6.
Okay.
When we were talking about how the Bootstrap works well for smooth statistical functions, and when we showed that example of when it didn't work well with the order statistic, but we did show that with parametric it was okay. So is this statement Bootstrap works well, or the non-parametric Bootstrap works well for? Yeah, I mean, I think the problem is that f hat is a discrete distribution. And then when you're working with then that corresponding non-smooth statistic, that's where the problem comes in. So, but it's only a problem with the non-parametric Bootstrap, not with the parametric, or is that just for that example?
I guess I've never really thought of it in that context of, well, normally we do most of the stuff in terms of the non-parametric. Parametrics, there are some nice problems that can be solved. But often the parametric Bootstrap is there to help explain what's going on. And I hadn't really thought of that in terms of maybe with a non-smooth statistic the parametric will work. Obviously it does in this particular case. I would think for a non-smooth statistic that parametric would work. What page is that?
26 is where you summarize.
Okay. Just out of curiosity before I leave, or before we leave, anybody heard of an influence function before? You've heard of an influence function? Where?
Regression.
In regression?
Well, it's like, I guess we would just talk about influence statistics.
Okay. Yeah. So like setting.
Yeah.
Okay. Yeah. That's going to be something different. So we're going to be talking about something called an influence function. Influence functions are used in what's called robust statistics, that area. We're not interested in robust statistics in this class. Rather, we're interested in some results that come about, and the influence function happens to appear. And so that's why I was just curious if some of you have had experience with influence functions before. So anyway, you'll see what influence function is the next time. So that's it.